Good evening, Professor Claudia Alberto Moreno and fellow students. I'm José Esteban Peña Rincón, and along with my teammates Manuela Zanabria Pacheco, Vanessa Rivera Guerrero, and Samuel Eduardo Manrique, we are presenting today on heat engines. We will be focusing on unique piece of thermodynamic brilliance, the Stirling engine. The Stirling engine is a remarkable advancement, but it is not new. It was invented in 1816 by Reverend Robert Stirling with a clear goal to offer a safer, more reliable alternative to the dangerous steam engines of the era. Its major advantage is that it uses an external heat source, allowing it to operate on any type of energy solar, nuclear, combustion, etc. The high theoretical efficiency of the Stirling, superior to standard steam, is its defining characteristic. This is due to its incorporation of a regenerator to recycle the heat that will otherwise be wasted between the hot and cold phases. This recycle allows it to approach the maximum efficiency limit. The Carnot cycle makes it one of the most theoretically efficient heat engines possible.
The Stirling engine is an external combustion regenerative closed-cycle engine. It is operated by cyclic compression and expansion of air or another gas, the so-called working fluid, at different temperature levels such that a net conversion of heat energy to mechanical energy occurs, or more specifically, a regenerative closed-cycle heat engine with a permanent gaseous fluid, where the closed cycle is defined as a thermodynamic system in which the fluid is permanently contained within the system, and regenerative describes the use of a specific type of heat exchanger and thermal storage device known as the regenerator. This inclusion of a regenerator is what distinguishes Stirling engines from other closed-cycle engines. This system consists of a cylinder with two pistons on either side and a regenerator in the middle. The regenerator can be a wire mesh, ceramic, or any type of porous block with a high thermal mass times specific heat, used for the temporary storage of thermal energy. The mass of the working fluid contained within the regenerator at any given time is considered negligible. The left chamber contains all the working fluid, a gas, at high temperature and pressure. During process 1-2, heat is added to the gas at high temperature from a source at high temperature. As the gas expands isothermally, the left piston moves outward, performs work, and the gas pressure decreases. During process 2-3, both pistons move to the right at the same speed to maintain constant volume until all the gas is introduced into the right chamber. As the gas passes through the regenerator, heat is transferred to the regenerator and the gas temperature decreases from high temperature to low temperature. For this heat transfer process to be reversible, the temperature difference between the gas and the regenerator must not exceed a differential amount at any point. Thus, the temperature of the regenerator will be hot temperature at the left end and low temperature at the right end when state 3 is reached. During process 3-4, the right hand piston moves inward and compresses the gas. Heat is transferred from the gas to the sink at temperature low temperature, so the gas temperature remains constant at low temperature while the pressure increases. Finally, during process 4-1, both pistons move to the left at the same speed to maintain a constant volume and push all the gas into the left chamber. The gas temperature rises from low temperature to high temperature as it passes through the regenerator and absorbs the thermal energy stored there during process 2-3. This completes the cycle.
Hi, my name is Vanessa. Today I will explain the four thermodynamic proposals associated with the Stirling cycle. I will also describe the temperature entropy diagram and the pressure volume diagram. Process 1, isothermal expansion. In the first process, the working gas expands isothermally at a high temperature. Heat is added to the gas from an external source. Process 2, isochoric regenerated coolant. In this process, the gas is cooled at constant volume inside a regenerator, and then heat is transferred to the regenerator for a temporary discharge. Process 3. Isothermal compression. In the trick process, the gas is compressed isothermally at a low temperature. Heat is rejected to cold reservoir. Process 4 is isochoric regenerated heating. Finally, in this process, the gas is heated at constant volume using the energy stored in the regenerator. So we had the PP diagram and TDS diagram. Okay, the PP diagram shows pressure versus volume. The Stirling cycle appears as a closed loop made of two horizontal and two vertical processes. And the TDS diagram shows temperature versus entropy. The isothermal processes appears as horizontal lines, and the regenerative processes appears as a vertical line. So, okay, in summary, the Stirling cycle is composed of four reversible processes and its diagrams help us understand heat transfer and work interaction in the system. So I am going to show an example of how a simple thermal machine works. Surely the exchange of energy will to thermal reservoirs. Initially, state 1, the air is at ambient temperature and pressure. When the flame is ignited, the air is heated and constant volume in the first cylinder until it reaches about 1 here Celsius, thus is increasing is pressure. State 2. From this point, the first piston moves at constant temperature, increasing the air balloon and decreasing the pressure. State 3. The air then enters the second cylinder, which is at ambient temperature, reducing the air temperature at a constant volume. State 4. The second piston moves back, compressing the air at this temperature and returning the air to the hot cylinder and state 1, from which the processor repeats. Yeah.
Okay, I'm going to explain the types of the Stirling engine. The gamma type. The gamma type Stirling engine operates by cyclically heating and cooling accelerated working gas, causing it to expand and contract on to drive its mechanical components. In this design, the displacement piston moves the gas back and forth between the hot and cold regions, while the working piston produces the mechanical power of the engine. Heat is applied at the top of the system through the heater, which warms the gas inside the upper chamber, known as the hot zone. As the gas in this hot zone expands, pressure increases and acts directly on the working piston, pushing it outward and delivering useful work to the crank mechanism. When the crank rotates, it's causing the displacement pistons to move in a away the gas is forced downwards into the cooling region. Before entering this cold region, the gas flows through the regenerator. A component designed to temporarily store heat from the gas is it moves toward the cold zone and return that heat when the gas moves back to the hot zone, improving the engine's thermal efficiency. Once the gas reaches the cold zone, it passes through the cooler, which extracts heat from the gas and raises the temperature and pressure. This cooling allows the work piston to move back and roll more easily as the crankshaft continues its rotation. The stem and run connect the piston of the rotating mechanism, ensuring that the motion the piston remains properly phased. The bush reducing the friction in the rotating joints, improving smoothness and efficiency. All of this motion is synchronized by the shuttle clock, which means the characteristic 19 degrees phase difference between the displacement piston and the working piston. This phase difference ensures that the gas is always transferred to the correct region, hot or cold, at the appropriate moment in the cycle, as long as a temperature difference is maintained between the heater and the expand cooler. The gas will continue to expand and contract in a repeating cycle, driving the piston and producing continuous rotational motion. This makes the gamma type Stirling engine simple. The beta type. The beta type Stirling engines operate by cyclically heating and cooling on a Stirling working gas, causing it to expand and contract in a way that drives the mechanical components of the machine. At the top of the system, the heater supplies external heat to the gas located in the expansion space, increases temperature and pressure. When the gas expands, it's pushed down of the power pistons, which is responsible for producing useful mechanical work. As the power piston moves, it transfers this motion to the rod, which then drives the crank inside the carter, converting the piston's linear movement into continuous rotational motion. Beneath the power piston is the displacer piston, which does not produce power but instead shifts the gas between the hot and cold sections of the engine. When this display piston moves upward, it forces the gas to travel downward in the cooler and into the compression space, where the gas releases to the surrounding and pressure decreases. When the pressure drops, the power pistons pull it upward more easily by the crank mechanism. On the way from the expansion space to the compression space, the gas passes through the regeneration, a porous thermal storage element that absorbs heat from the gas as it moves toward the cooler and returns that heat when the gas travels back toward the heater. This significantly improves overall thermal efficiency. As the crank continues to rotate, it maintains a fixed phase difference between the displacer pistons and the power pistons, ensure that the gas is always moved to the correct region at the correct moment in the cycle. The engine repeats this sequence continuously. The heater warms the gas, the power piston extracts from the expansion, the displacer shifts the gas into the cooler which contracts, and the crank mechanism coordinates the timing of both pistons. As long as temperature difference is maintained between the heater and the cooler, the engine will continue producing smooth, relieved power. The Alpha Stirling engine. The Alpha Stirling engine functions by cycle heating and cooling a fixed amount of a gas such as air or helium, shooting it between a hot and a cold cylinder to generate power. In the peak dead engine, the process begins in the hot volume, where an external heat source heats the gas, causing it to expand. This expansion forces a full drives the hot piston down routes. The expanding hot gas interforced through the heater and into the regenerator. This case component acts as a thermal sponge, absorbing heat from the gas as it passes through, which cools the gas on this way the cool side. The now cooler and contract gas enter the cold volume, where the cooler funnel exerts heat, lowering the gas pressure. This low pressure state allows the cold piston to move upward easily, compressing the gas and pushing back through the system. On this return journey, the gas passing back through the regenerator, where it reabsorbs the stored heat, becoming pre-warmed before it re-enters the hot volume to begin the cycle again. The phasing motion of the two pistons, often connected to the crankshaft at a 90 degrees angle, ensures the cycle repeats continuously, converting the thermal energy into useful mechanical work. Okay, I want to next with the applications. Meaning, the Stirling engine was primarily invented for pumping water in mines. Since these mines were located far from cities and were poorly developed, and the simplicity of the Stirling engine allowed them to pump water using this device and perform maintenance on it even very basic knowledge, or even well it themselves thanks to its simplicity. Unfortunately, this simplicity affects the engine's performance, as it could not generate the same flow rate as the same engine of the time. However, today things have changed, and it's possible to achieve very good performance and great safety compared to the steam engine. Submarines. The application in submarines did indeed take place. The submarines developers were looking for engines that did not require oxygen to generate explosion and could extend the time the crew could stay underwater. In 1988, the sub company installed a liquid oxygen system and Stirling engines in its submarines. The efficiency of this engine, which extends underwater endurance from the weeks to months, leads the Swedish Navy to equip almost all for its Gotland class submarines with this type of engine today. They still have 5 units in operation due to their great reliability and efficiency. Refrigeration. The use of Stirling engines in refrigeration is one of the most common applications today. This is based on reversing the operation of the Stirling engine using in previous applications. Now, instead of applying heat to the engine's hot source, mechanical energy is applied to the piston so that the engine absorbs heat. This is the most efficient when dealing with extremely low temperatures, such as cryogenics, reaching temperatures as low as 22 Kelvin. Very low temperatures that are currently used for cryogenic applications will continue today.
The Starling engine stands as a thermodynamic masterpiece, defined by its independence from the heat source and its exceptional efficiency, operating through external combustion. It offers unparalleled full versatility. Scientifically, its ideal cycle is a model of rigor structured by two isothermal processes that maximize work and two isochoric processes where the crucial regeneration functions. Recycle head to ensure the system asymptotically approach Carnot cycle efficiency. This regenerative dexing is not merely a feature, but the principle that elevates the Stirling from a simple thermal engine to a machine that utilizes intelligent head management as its highest expression of efficiency.